Hello there, and welcome to the planet's memory, where science moves slowly, softly, and sometimes in circles. This is a place for wonder that doesn't shout, for questions that echo gently through the dark, and for stories that feel more like dreams than answers. If you're the kind of person who likes to fall asleep not to silence, but to slow-burning curiosity, you're in the right place. Tonight, we're going to drift together into a mystery older than anything we know. Not a mystery of gods or ghosts, but of molecules and memory, of fossils and stars. Before we begin, I'd love to know, where are you listening from? Somewhere quiet? Somewhere where the sky feels wide and ancient? Wherever you are, let this be a small ritual of rest. If you find yourself enjoying this journey, if it calms you, stirs something soft inside you, feel free to like or share. It helps this tiny tide of stillness reach other curious minds in the night. Now let's begin slowly, like the unfolding of something fossilized. What if we are older than Earth? It sounds like poetry, like something you'd find scratched on a forgotten tablet or whispered in a dream. But it's also a question some scientists have dared to ask. Not because it's easy, but because the evidence doesn't quite make sense unless you stretch your imagination beyond Earth itself. Life appeared on our planet fast. Too fast. The earliest signs of life, tiny, primitive microbes, show up in the rocks not long after the Earth cooled enough to support oceans. Not millions of years later. Not even hundreds of millions. Just there. As if life was waiting. As if it arrived already packed and ready, seeded from somewhere else. This is where the theory of panspermia begins. The idea that life didn't originate here, but traveled, sleeping and silent, across space. Maybe on meteorites, maybe on the dust of ancient comets, maybe even in clouds of gas that drifted between stars long before our sun was born. And if that's true, if even the tiniest fragment of that is true, then our story is not just Earth's story. It is a galactic one, a memory scattered among stars. Let's imagine it together. Long before this planet had continents or clouds, long before volcanoes breathed or oceans sighed, somewhere, far away, something lived. It lived, it died, it decayed. But in its decay, it left behind a molecule, a shape, a blueprint. And that shape did not stay still. It floated, not because it wanted to, not because it had a mission, but because the laws of physics carry things the way wind carries seeds. And so the seed drifted. Perhaps it froze inside a meteorite. Perhaps it was shielded by stone, wrapped in time like a fossil before it even reached Earth. Perhaps it tumbled through space for millions of years. Perhaps billions. Through quiet, starless nights. Through storms of radiation. Through the gravity of passing giants. It waited. And then, it landed. Maybe it struck the young Earth during a period of chaos and fire. Maybe it nestled into a warm pocket beneath the crust, or sank to the bottom of a boiling sea. And perhaps, in just the right temperature, with just the right chemicals, in just the right silence, it woke up. Not like an animal wakes, not like a dreamer, but like a pattern remembering how to repeat itself. Not life as we know it, but life as potential. We see echoes of this in the chemical record. Amino acids, the building blocks of life, have been found on comets. Organic molecules lie frozen in the black hearts of meteorites. And tiny, ancient bacteria, so simple and yet so persistent, can survive vacuum, radiation, and deep freezing. Earth didn't invent life's ingredients. It simply baked them into form. And that changes something. Not just about biology, but about identity. If life came from elsewhere, then so did we. If our earliest ancestors were born in the heart of a dying star, or the crust of a long-lost planet, then the line between alien and human dissolves. We are not a product of Earth. We are passengers. We are memories wrapped in flesh. And maybe that's why we feel awe when we look at the stars, because some part of us remembers. Not in words, not in stories, but in structure, in the shape of our proteins, in the rhythm of our cells, in the dust inside our bones. What if your blood remembers a sky that no longer exists? What if the impulse to look up isn't wonder, but homesickness? Of course, we can't prove it. Not yet. Science moves slowly, like continents, like glaciers. But every time we crack open a meteorite, every time we listen for chemical signals on distant exoplanets, we are tracing a thread back in time, a thread we might someday follow to our oldest self. And if that self wasn't born here, what does that make Earth? A cradle? A refuge? A second chance? We may never know. But in the quiet space between not knowing and imagining, something beautiful happens. Not answers, but questions that feel like dreams. And yet, if this much can be lost, what else might we have forgotten? We often imagine Earth as the beginning, the birthplace, the origin of everything that breathes, pulses, or remembers. But what if Earth is not the first cradle of life, only the one we woke up in? What if, long before this planet turned green, long before its mountains were raised and worn down, other worlds had already bloomed and ended, quietly, completely, and left no one to tell their stories? It's a thought that drifts on the edges of science and speculation, but not without evidence. The galaxy is ancient, the universe older still. Stars have been forming and dying for billions of years before our sun ever lit the sky. And around many of those stars, planets once circled, warm, rocky, oceanic. Some of them may have held the right chemistry, the right atmosphere, the right quiet for life to stir. Not fantasy, just timing. The cradle before the cradle. A place that once held the spark we now call our own. Could life have begun elsewhere and ended? Not in fire, but in silence, before drifting toward Earth? Not as spaceships or stories, but as dust, as dormant fragments, as frozen codes carried in the bellies of ancient rocks. Meteorites, after all, are not just stone. Some are time capsules. In them we found amino acids, nucleobases, organic molecules that hint at biology, or at least the handwriting of it. They arrive here still whispering of their former homes. Not loudly, not clearly, but like a letter smudged with distance and age. We've held pieces of other planets in our hands. Some, we know, came from Mars. Others, perhaps, from long-dead bodies that no longer orbit any sun. What else might they carry? What memories might be frozen in those fractures? What blueprints might lie dormant, waiting only for the warmth of a new world to awaken? It's possible, scientists say, for microscopic life to survive the journey through space. Shielded deep within a rock, some forms of bacteria can endure radiation, extreme cold, and the long sleep of interstellar drift. And if they survived impact, even just a few, they might have seeded something new in Earth's early oceans. Not because they meant to, but because conditions said yes. Life, in this view, is not a miracle of one world, but a traveler. Not rooted, but drifting. It follows chemistry. It follows energy. It follows shelter. And maybe it follows endings, too. Because for one cradle to give, another must be ready to receive. We tend to think of extinction as an end. But what if extinction is sometimes an act of giving? What if the collapse of one biosphere becomes the carrier of life to another? What if some planets are born to hold life briefly, only to pass it along in the moment of their death? Could it be that life has passed through many hands before ours? That our planet is just the latest to host the same long, slow experiment? These are not fantasies. They are questions with roots in geology, in chemistry, in the ancient trails of isotopes and elements. The more we study Earth's oldest rocks, the more we find signs that life began very early, suspiciously early, as if it did not need to evolve from scratch, but merely continue. And so we look up, not with hope for rescue or fear of aliens, but with quiet wonder. Wonder at the possibility that we are part of a migration, not just a creation. That Earth is not a beginning, but a chapter. A chapter in something wider, older, slower. Maybe life comes and goes like tides across the galaxy, rising on one world, falling on another, carried by stone, by time, by the patient gravity of stars. Maybe Earth is not the only place to wonder who we are. And if that's true, if we are not the first or the only or the origin, then the silence between stars is not empty. It is waiting, waiting for the next cradle to open, waiting for the next memory to take shape. And yet, if we carry remnants of older worlds within us, then perhaps the molecules of our blood still whisper of skies we never saw. When you look up at the night sky, you're not just seeing light. You're seeing history. You're seeing what's left after stars have burned, collapsed, wandered. You're seeing dust, soft, ancient, cosmic dust, floating through the darkness like ash from a forgotten fire. And hidden in that dust is something more. Deep in the frozen bones of comets and the drifting skin of asteroids, scientists have found something strange. Something small and quiet and vital. Organic molecules, amino acids, the gentle curves of carbon-based forms. Not life, not yet, but the pieces that could become it. The first sketches, the silent blueprints. They aren't rare. In fact, the universe seems to be littered with them, scattered across interstellar clouds, frozen into meteorites, embedded in comets that orbit our sun like ancient messengers with nowhere left to go. These aren't Earth's inventions. They existed long before Earth had oceans or oxygen or even a name, and that's what gives scientists pause. Because these molecules are not easy things. Their structure is precise. They aren't the kind of randomness that wind or erosion might create. They are patterns. Patterns with purpose. And we carry nearly the same ones inside us now, in our cells, in our enzymes, in the memory of what life decided to be. What if the ingredients for life were not born here, but arrived like seeds? What if they were carried, slowly, silently, across light years, tucked into the icy shadows of comets? Not to spread life, but simply to survive. To endure the long sleep between stars? We've already found glycine, the simplest amino acid, in space dust. We've found it in the coma of comets. We've found complex hydrocarbons on meteorites. And with each discovery, the line between Earth life and cosmic chemistry becomes more like a suggestion than a wall. Think about this. Every time a meteor blazes through our sky, it leaves behind a trace. Not just heat or light, but elements, molecules. Some burn up, but some do not. They drift downward. They land. They mix into soil. They sink into oceans. Some of those fragments, billions of years ago, may have carried the first tools of life. Not plans, not architecture, but a language waiting to be spoken. Perhaps Earth didn't invent life's alphabet. Perhaps it simply listened well. The early Earth was not a calm place. It boiled and trembled, collided with other bodies. It rained molten stone, and later it rained comets, frozen travelers rich in carbon, water, ammonia, and potential. Each impact a violent offering. Each one leaving behind more than just craters. Could it be that, in those chaotic early centuries, the foundation for biology was being gently stirred into the crust? Mixed into the ocean? Sheltered in thermal vents and quiet pools where entropy slowed and molecules had time to touch? It's possible. And that possibility reshapes everything we think we know about our origins. Because if these ingredients came from space, then life is not the miracle of Earth alone. It's the echo of something older, something widespread, something that prefers quiet pockets of order in a universe ruled by chaos. Life, in this view, is not rare. It's inevitable when the right dust finds the right home. And there's something else. A kind of humility in knowing we may not be original. That even our deepest biology might be borrowed. Not stolen. Not imposed. Just shared. Like a story passed along. Rewritten slightly with each new listener. Maybe that's what these molecules are, memory in its earliest form. Not memory with thoughts or images, but memory as structure. Memory that repeats itself because it knows it works. A spiral of sugar and phosphate that refuses to forget how to hold information. That's what DNA is, after all. A molecule that remembers. A molecule that can be copied and passed down, over and over, like a song with no beginning and no end. And its raw components, the notes and rhythm, may have come from stars. From clouds of dust. From comets we've never seen. Some of that dust is still falling now. Slowly. Softly. Each year, Earth collects about 40,000 tons of it. Most of it burns. But not all. Some finds its way into oceans, into soil, into the roots of plants and the breath of animals, perhaps even into us. You are made of earth, but also of things that drifted here before earth was ready. And that idea that you are built from blueprints written in the silence between stars is not fantasy. It's chemistry, it's geology, it's physics slowed to a whisper. So the next time you see a shooting star, don't make a wish. Ask a question. What if that flash of light once carried the seed of life? What if some part of you came from it? And yet, if this dust could carry life, what else might it carry that we've never thought to look for? The earth has no voice, and yet, it speaks. Not in sound, but in structure, in patterns, in ratios, in elements that change so slowly, their passage feels more like memory than motion. This is the language of isotopes. Quiet, steady, unfailingly patient. It lives in the deepest rocks and the oldest sediments. And if you know how to listen, it can tell you when something happened. And maybe, if you listen just a little more softly, it can tell you when something should not have happened at all. Isotopes are versions of the same element with different weights. Carbon, uranium, nitrogen, all have heavier and lighter siblings. They behave nearly the same in chemistry, but in time they part ways. Some decay, some linger, some become something else entirely. Through this slow unraveling, we begin to tell time not in hours or years, but in half-lives. In the fading presence of radioactive parents and the quiet emergence of their daughter elements. Each rock becomes a clock. Each layer of earth a page in a story no one meant to write. And within this story, there is something puzzling. In the oldest rocks we've found, those formed just after the earth cooled, there are signs of life. Tiny isotopic fingerprints left behind by ancient microbes. Ratios of carbon-12 to carbon-13 that don't appear by chance. Signatures that suggest biological processes, active and persistent, more than 3.8 billion years ago. But Earth itself was still reeling, still young, still boiling in parts, still being bombarded by comets, by debris, by radiation. It had just emerged from the chaos of its own formation. How, then, could life already be here? This is where the language of isotopes raises its voice. Because if life was already present in that early chapter, then either it formed impossibly fast, or it didn't form here at all. It arrived. The carbon isotope ratios in ancient graphite hint at metabolism, the kind of selective processing only living things perform. The sulfur isotopes in old sediments suggest early microbial respiration. Even the presence of certain nitrogen isotopes tells us there were life forms manipulating their environment, adapting, surviving. And the deeper we go, the more this timing seems strange. Life, it seems, did not tiptoe into Earth's story. It stepped in as though it had been waiting, as though the moment the planet calmed, even slightly, it unfolded, not as invention, but as continuation. Could this be evidence of panspermia? Of ancient spores carried here long before the Earth was ready, waiting in silence, embedded in rock or ice, until the planet could provide shelter? Maybe, maybe not. But the isotope trails are hard to ignore. They don't scream. They don't insist. They just persist, like echoes of something forgotten, but not fully erased. Even the zircon crystals, the oldest minerals we've found, carry traces of life's presence. Inside their lattices are chemical anomalies, signals of water, signals of carbon, signals of a world already becoming alive while it was still becoming a world. There's something humbling about that we can look at atoms today, at their slight differences in mass, and hear the rhythm of life pulsing through stone. That we can hear a whisper across billions of years saying, I was here, I left this mark, I shaped this ratio. And that whisper does not come from fantasy, comes from math, from physics, from the science of decay, and the art of patience. Isotopes don't lie. They can be misread, but they do not invent. They are memory crystallized. And they remember a time when life existed before we thought it could. So what do we do with that? Do we revise the timeline of biology? Or do we accept that biology may have arrived from somewhere older, somewhere already shaped by stars we'll never see. If life didn't begin here, then these isotope signatures are not just ancient, they are imported, preserved like cargo, silent until read. And if so, what else might be hiding in ratios we haven't yet understood? There are stones that fall from the sky, stones older than the earth itself, stones that were born in silence, shaped by heat, and cast adrift into the long, cold dark, waiting not for destiny, but for collision. We call them meteorites, and we gather them as if they were sacred, because in a way they are. These are not just rocks. They are time travelers, messengers, fossils of the cosmos, each one a fragment chipped from something ancient, the core of a long-dead planet, the crust of a shattered moon, the dust ring of a forgotten star system. When they land, they do not ask for attention. But those who study them know they have stories written in their structure. Meteorites remember fire. They remember the searing heat of their birth, formed in the swirling chaos of the solar nebula. They remember the violence of ejection, torn from their homes by impact, hurled into drifting exile. And they remember the moment of arrival, the burning rush through Earth's atmosphere, the sudden silence of landing, the cold stillness of being found. And inside they may remember something more, a molecule, pattern, a shape so simple it could fit in the tip of a needle, and yet so complex it could spiral into life. Scientists have sliced open these skyborne stones, peered into their cores, and found the whisper of organics. Amino acids, hydrocarbons, the curved shadows of carbon structures not made here, but carried, delivered, offered maybe by accident, maybe by design. We don't know, but we listen. One such messenger, the Murchison meteorite, fell in Australia in 1969. It scattered debris across a quiet field. But inside its blackened fragments, researchers found over 70 amino acids, many not known on Earth, others precursors to molecules we know as life, and their isotopic ratios, not terrestrial, not familiar, not local. Could the stone, or one like it, have carried the first instructions for life? Not blueprints exactly, but sparks, because fire doesn't always come in flames. Sometimes, fire is the moment when a molecule finds another that fits, when chemistry becomes persistence, when random becomes repetition. That's the moment when matter begins to resist entropy, when it begins to remember, when it begins to change its own future. And if that fire began in a stone not of this earth, then so did we. Perhaps it wasn't just one meteorite. Perhaps it was thousands, over millions of years, layering potential into Earth's crust like a kind of genetic snowfall. Some burned away, some dissolved in water, some settled into clay or thermal vents and waited. And when the moment was right, when the soup was stirred enough, when the planet cooled enough, when time allowed it, the pattern unfolded. Not because it was destined, not because it was designed, but because the ingredients refused to remain separate. And that refusal, that memory of combination, may have been written first inside a stone. It's humbling to think that the first true step toward life could have arrived inside something so dense and silent, so seemingly inert. But meteorites are not dead. They are libraries, compressed by gravity, etched by radiation, preserved by vacuum. Their surfaces are scarred by collision, but inside, they hold chemistry untouched for billions of years. And when we crack them open, we are not just looking back. We are looking outward. We are asking, softly, whether the fire that lit our biology might still exist elsewhere, inside some drifting fragment still orbiting the stars. Could life be waiting again, in another stone? Somewhere, across the lightless divide between systems, is there another rock carrying the same spark, the same silent fire, bound for another cradle? If we held it, would we recognize it? Would it feel familiar in our hands? Or would we miss it, mistaking life's earliest message for noise? Perhaps we already have. Perhaps the fire has touched this planet more than once. Perhaps it is still touching us. And yet, if even stones can remember fire, what other memories might be buried in the bodies of stars? There are theories that shout and theories that hum. Panspermia is the latter, a theory that floats. Not heavy with certainty, not loud with proof. Just quiet, persistent, like dust in sunlight. It suggests that life did not begin on Earth, but arrived, drifted, fell. Life not born in place, but scattered through space like seeds on the wind. To some, it sounds like science fiction. To others, it is a scientific riddle hiding inside cosmic possibility. But either way, it invites something rare, a reason to wonder. The idea has ancient roots. Even before microscopes and molecules, philosophers asked, could life move from one world to another? Could creation be an active journey, not of origin? Today, we know a little more. We know that space is not empty. It is filled with dust, gas, comets, debris. It is filled with stone and silence and time. And tucked inside some of those stones, as we've seen, are organic molecules, the rough syllables of life's language. The question panspermia asks is gentle but profound. If those syllables can survive the vacuum, the cold, the radiation, how far might they travel? We already know that microbes on Earth can endure extremes. Some live in boiling vents at the bottom of the ocean. Others sleep inside salt crystals for millions of years. Some survive doses of radiation that would sterilize entire ecosystems. A few, tested in space, endured the void itself. Not thriving, but persisting. Waiting. So, could they float? Could a single-celled organism, frozen inside a rock chipped off Mars or another world, survive a journey across space? Not for years. Not for centuries. But for tens of millions of years? It's not impossible. And that word, not impossible, is often where science begins to listen. Because the physics checks out. Rocks can be ejected from planets after impact. Some of them escape gravity. Some drift. Some, by chance, fall onto another planet. It's called lithopanspermia, stone-born life. Mars and Earth have likely exchanged material. We've found meteorites from Mars here. We've held them, measured them, sliced them open. If microbes existed on ancient Mars, could they have come here first? Could Mars be our biological ancestor, even if Earth is our home? We also look further, beyond planets, into the interstellar dark. Radiopanspermia wonders if microscopic life, light enough to be carried by solar winds, could drift between star systems. Not fast, not directly, but eventually. There's no proof, but there's no law that forbids it either. The theory doesn't claim intention. It doesn't say life was sent. It says life may simply go because gravity allows it, because chemistry is patient, because time is long. And over those long scales, geological, stellar, galactic, what seems rare becomes likely. 1 trillion spores flung into space. Most perish. Some drift forever. One lands. One finds warmth. One stirs. And that may be enough. This version of panspermia is not about intelligent design or alien architects. It's about resilience. It's about how life, once formed, does not give up its shape easily. It clings. It travels. It hides in cracks and shadows, in the porous belly of rock. It lets time do the rest. There are, of course, critics. Rightfully so. Panspermia shifts the question, but does not answer it. If life came from elsewhere, where did it begin? If not Earth, then what was the true first cradle? The theory doesn't pretend to know. It only suggests that life may be older than this world, and more mobile than we thought. That the universe is not a place where life happens, but where life moves. And in that movement, something beautiful emerges, the idea that we are connected not just to this planet, but to others. That our story is not singular, but shared. That life may be a thread woven through multiple worlds, carried across epochs of dust and distance. Could spores sleep their way across space? Could life rest inside a comet's icy core, waiting for a sun to pass too close? Could we be the continuation of a story that began in a different sky? Maybe, maybe not. But the beauty of panspermia lies not in certainty, but in perspective. It reminds us that life is not fragile. It is persistent. It is a pattern that wants to repeat. And whether it began here or elsewhere, the fact that it exists at all, that it exists in us, is enough to keep asking. And yet, if life is capable of drifting so far, what other seeds might be sailing past us right now, unseen? Not all journeys end in welcome. Some end in fire. Some end in fracture. Some end in nothing at all. And yet, somewhere in Earth's long past, a journey that began in the cold stillness of space may have ended in just the right way, not in destruction, but in survival. If life truly arrived here from elsewhere, carried inside a meteorite or clinging to dust, then it did not drift gently onto soft soil. Crashed. It burned. It met Earth with violence. The moment of entry is not kind. Imagine it. A small rock, no larger than your hand, tumbling into Earth's atmosphere at tens of thousands of miles per hour. The air ahead of it compresses so suddenly, so violently, that it becomes fire. The surface of the rock glows white, then orange, then blackens into ash. It may break apart. It may shatter. It may never reach the ground. And yet, sometimes it does. Some meteorites survive the descent, their insides untouched by flame, shielded from the heat by layers of molten crust, like a hard shell guarding something fragile inside. Could life survive such a fall? Could a bacterium, small beyond imagination, tucked in a crack of stone, endure the pressure and heat and still remain viable? The science says, maybe. Under the right conditions, it is not only possible, it's been demonstrated. In laboratory settings, microbes have survived simulated impacts. They've endured shock pressures and re-entry temperatures, especially when buried beneath the surface of protective material. Some of them reawaken. They begin to grow again, as if nothing happened. They do not scream. They do not announce their arrival. They simply continue. And that continuity is the miracle. Life is not fragile in the way we often think. Individual organisms are delicate, easily destroyed, easily lost. But the pattern of life, the recipe it follows, is persistent. It finds ways to endure. It seeks stability in chaos, shelter in fracture. And sometimes that shelter is a rock. If a single microbe survived the fall, just one, it could begin the slow process of replication. If conditions allowed, it might find warmth, moisture, food. It might divide, multiply, and over time evolve. But the odds were slim. The early Earth was not a gentle place. Volcanic, storm-lashed, bombarded by more impacts. Radiation from the young sun poured down without the protection of an ozone layer. Oceans boiled. Continents were still dreams waiting to form. And still, the seeds may have taken root. Because the arrival didn't need to be perfect. It only needed to succeed once. All life on Earth, every tree, every cell, every breath, may trace back to that single successful landing. To one ancient spore that survived entry. To one brief pocket of safety in a world too young to care, but just old enough to allow. And we see reflections of that survival in the life forms we know today. Tardigrades, for example, microscopic creatures that can survive radiation, vacuum, extreme cold, and crushing pressure. Extremophiles that live in boiling acid. Bacteria that can remain dormant for millions of years. They remind us that survival isn't always about thriving. Sometimes it's about waiting. Sometimes it's about falling through fire and waking up anyway. So much could have gone wrong. The rock could have shattered. The heat could have sterilized. The pressure could have crushed every delicate chain of amino acids. But it didn't, or at least not every time. That's the quiet miracle. Not that life exists, but that it arrived and kept going. And when we look at meteorites now, cracked open in sterile labs, examined under microscopes, read like ancient scripts, we are asking again and again not just where they came from, but what they carried. Not just what they are made of, but what they once protected. Because if life has arrived here once, it may again. It may already have. And yet, if the fire of entry was not enough to end it, what else might life have survived before ever reaching us? Time, we think, moves forward, straight, predictable, one second after another, always into the future. But when we look into Earth's deep past, into the bedrock of memory, time begins to shift. It stretches, bends, loops softly in the dark. And if life began before Earth was fully formed, then time, as we know it, may not be the story's first author. Imagine a single-celled organism older than mountains, smaller than a grain of dust, drifting through black space, asleep inside a rock. It has no clock, no hunger, no fear, just a coil of potential tightly folded, a recipe for persistence. This is the abyss of time, not a place, but a silence. A space where life may have waited not for days or centuries, but eons. Where survival did not mean movement or breath or growth, but the refusal to decay, the choice to endure. Pause, longer than memory. When we study the oldest rocks on Earth, we sometimes find hints of that pause breaking. Microfossils, delicate impressions, smaller than dust, found in ancient formations like the apex chert of Australia or the Novwojitic belt in Canada. Carbon traces in layered sediment, shaped not by chance, but by biology. These are not large discoveries. They do not shout. They barely speak. But their presence is unsettling, not for what they tell us, but for what they suggest. That life existed almost as soon as it could exist. That it was ready, long before the world seemed capable of supporting it. Which leads us back to the idea we've been circling all along. What if life didn't start here? What if it arrived in full not as a spark but as a sleeper? Not as invention but as continuation. In that view, time becomes strange. Identity becomes strange. Because if life originated elsewhere and migrated here, then our lineage does not begin on Earth. It begins on another world, another timeline, one we can't touch, but may still carry within us. Every living cell is a kind of history. DNA is not just instruction. It's memory, shaped by need and experience. The more we study genetics, the more we see patterns that have lasted for billions of years. Not because they're beautiful, but because they work. They persist. And maybe persistence is identity. Maybe who we are, not as people but as life, is not defined by consciousness or language or intelligence, but by the ability to remain, to adapt, to carry forward a thread that began so long ago it feels like mythology. This idea unsettles our sense of origin, because we like the thought of beginnings, of creation, of something starting fresh. But panspermia, and the possibility of pre-Earth life, offers something else. Not a birth, but a memory carried forward. A migration of identity not through culture, but through molecule. Is it possible that the same forms of life or fragments of them have visited many planets before this one? Not with intent, not with direction, but like spores in the wind, falling where they may, surviving only where the world agrees. Could there be versions of us, not in form but in chemistry, scattered across the galaxy? Maybe, maybe not. But the longer we sit with this thought, the more it begins to feel soft around the edges. Not threatening, not cold, just vast. Like time itself, there is something oddly comforting in knowing that life may be older than Earth. That our identity may be part of a much larger chain. That we are not singular, but part of a pattern that flows across planets, across stars, across the slow collapse and rebirth of galaxies. Life in the abyss of time doesn't rush. It does not seek the shortest path. It drifts, pauses. It waits until the conditions are right, and then it begins again. As if the story could never be erased, only retold. And if that story is still being told through us, then we are not the destination. We are a chapter, a page in something wide and unhurried. And yet, if identity can stretch across time like this, how far across space might it reach? There are fossils we expect to find. Trilobites curled in ancient stone, fern shadows etched into shale, bones half lost to sediment and time. And then, there are the ones we've never found, but still wonder about. Technofossils. Not the bones of creatures, but the remnants of tools, of machines, of intention, the residue not of biology, but of intelligence. Could something long before us, not human, not known, have touched this planet and left no trace, except the kind of trace we don't yet know how to see? This is not a theory loud with answers. It is a soft question that hums beneath geology. Could Earth hold within it the remnants of a civilization not born here, or even perhaps born here, but so long ago that its evidence has eroded into silence? We measure civilizations in metal, plastic, radiation. But these signals don't last forever. Entropy eats even memory. Cities fall. Satellites decay. Skyscrapers return to dust. And on the timescale of geology, millions, even billions of years, even the boldest artifacts vanish. Plate tectonics fold continents into themselves. Oceans rise and dissolve coastlines. Volcanic ash buries valleys. Ice scrapes the surface clean, over and over, again and again. If a technological species existed on Earth before us, say 100 million years ago, would we even know? And if something visited from beyond, not with fleets or flags, but with subtlety, could it have come and gone without leaving a visible scar? This is where the idea of technofossils begins. Not fossilized tools, not spacecraft buried under stone, but chemical signatures, unusual isotopes, synthetic molecules that don't form in nature. Tiny, unassuming anomalies embedded in ancient rock layers. Things we might not think to look for or recognize because they don't fit the timeline we assume. One such mystery exists already. A layer of rock, thin but global, contains a spike of iridium, a rare metal on Earth's surface, but common in asteroids. It marks the boundary of the Cretaceous and Paleogene periods, the moment when a massive impact likely ended the age of dinosaurs. The iridium wasn't left by life, but it left a story behind. What if something similar exists, hidden in the crust, but left not by a rock, but by intelligence? A nuclear signature, an anomaly in the carbon chain, a polymer without a biological origin. And what if we've already dug past it, unaware? The fossil record is a story written in erasure. Most life leaves no fossil. Most time leaves no trace. So why would we expect technology, already fleeting in our own age, to last deep into geological time? Plastic, for example, will eventually decay. Metal corrodes. Radiation fades. Cities sink. The Anthropocene, our current epoch, might leave little more than a dark line of carbon and debris in the strata. If we vanished today, how long before Earth buried the evidence of us? 10,000 years? A million? 100 million? Could another species, far in the future, ever guess we were here? And then we ask the quieter question, what if we are the future species, the one trying to guess? There is no clear evidence. No artifact dug from the mantle. No alien device weathered into myth. But absence is not proof. Silence is not denial. Entropy ensures that, given time, even the loudest stories disappear. But perhaps not entirely. Technofossils might still whisper in the deep, in rock cores, in mineral veins, in patterns of decay that don't match natural processes. And as our tools sharpen, as our models evolve, we may begin to hear them, or suspect them, or wonder seriously about the shape of a civilization that did not end, but faded, perhaps seeded, perhaps moved on. Some scientists have even asked, what if a civilization once used Earth as a nursery? Not to visit, not to conquer, but to plant something, to test conditions, to initiate life, and then leave. Not gods, not overseers, just participants in a long, quiet chain of causality. If such a thing happened 1 billion years ago or more, what would remain? Maybe nothing. Maybe everything. Maybe the only trace is in us, not in our tools but in our biology. In the way life adapted. In the timing of its emergence. In the mystery of its early leap. We don't know, but we listen. Because sometimes the most important fossils are not found in bone or stone, but in questions that refuse to go away. And yet, if a billion-year-old message was sent and lost, who or what might have been listening? Planets, like old friends, do not always speak in words, but sometimes they exchange pieces of themselves, not through conversation, but through collisions, through pressure, through force so sudden it fractures crust and launches stone into the sky. Rocks have moved between Mars, Earth, and the Moon, not by rocket, not by hand, but by ancient impact, A slow, violent choreography played out over billions of years. And this is where the quiet theory of lithopanspermia begins. The idea that life, or at least the seeds of life, could hitch a ride across space on rocks thrown from one world to another. It's not an idea born from science fiction. It's born from the rocks themselves, meteorites found here on Earth, traced chemically back to Mars. We've held Martian stone in our hands. It fell to Antarctica, to deserts, to quiet fields, carrying within it not just the dust of another planet, but the question of what it once touched. If rocks can move between planets, what else might move with them? Dust, molecules, microbes, maybe even memory, wrapped in carbon. It doesn't happen often. It doesn't need to. One impact large enough can launch fragments into orbit. Some escape velocity. Some drift for thousands, even millions of years until gravity pulls them back down. Not to their world of origin, but to a new home. In a cosmic sense, planets trade secrets. They swap material in silence. Not frequently, not on purpose, but often enough that we must wonder, what else rides along? Could a single-celled organism, tucked deep within a Martian rock, have survived the journey to Earth? Protected from radiation, asleep during the cold drift, reawakened only upon arrival? We've already seen extremophiles, Earth-based microbes, survive similar conditions in laboratories. Some endure pressure, heat, even vacuum. Others remain viable for millions of years in permafrost and salt. If life began on Mars first, or even differently, could it have reached Earth this way? Or could Earth have been the giver, not the receiver? Might early Earth, struck by an asteroid during its violent youth, have flung life-bearing rock toward the Moon or toward Mars? The beauty of lithopanspermia is not that it answers the question of origin. It unravels it. Because if life can travel between worlds, then the story of where it began becomes less important than the story of how it spread. Mars, Earth, the Moon, perhaps even Venus in its younger, more temperate days. A network of planets quietly sharing chemistry, sharing chances, trading life not like a treasure, but like pollen on the wind. And yet, we see no clear signs of life elsewhere. At least not yet. Mars shows promise. Methane traces, riverbeds carved in stone, sediment that hints at stillness and water. But no fossils, no motion, just silence. Still, the possibility persists. What if Mars was once alive? What if it shared its life with us? Or received it and then lost it? This is not science driven by spectacle. It is built on physics, geology, and observation. The trajectories of meteorites, the resilience of microbes, the timing of planetary bombardment, all suggest that lithopanspermia is not just plausible, it may be common. But here's what's most poetic. It means that life does not belong to a single planet. It belongs to systems, to relationships, to chance alignments where one world's loss becomes another's beginning. Maybe planets, like people, are not meant to be isolated. Maybe Earth's ability to host life is not a unique trait, but a shared inheritance. And if that's true, if life has passed between worlds like a traveler without borders, then every fossil, every cell, every breath we take is not just Earth's legacy. It is the echo of an ancient trade, a whisper passed between neighbors. And yet, if planets can carry life to one another, could they also carry stories far stranger? Stories we've never thought to imagine? Some forms of life do not live in the way we know it. They do not grow toward sunlight or seek warmth in shelter. They do not move or feed or even breathe. They wait. They endure. They sleep. In the still spaces of the planet, deep within ancient salt, beneath miles of ice, under the pressure of forgotten sediment, microbes have survived in stasis. Not for years, not for centuries, but for millions of years. Bacteria, preserved in halite crystals more than 250 million years old, have been revived. Microbes buried beneath Antarctic ice have stirred after eons in the cold. Spores entombed in amber or permafrost have returned to life when warmed, as if no time had passed at all. They sleep not as animals do, not in cycles or rhythm, but in the way a flame waits inside flint. Quiet, shapeless, but present. And that stillness invites a question. What does it mean to be alive? If life can persist without motion, what memories might remain inside these sleeping cells? Not memory as we know it, not thought, not emotion, but memory as molecule, as shape, as sequence. A memory written in DNA that survives even as all other signs of life have fallen away. When we think of fossils, we imagine bones and shells, the solid remnants of once living forms. But microbial life does not fossilize in the same way. It survives by retreating inward, shrinking, hardening, sealing itself away. A spore, after all, is not a body. It is a blueprint, a vault, possibility. Inside that vault, life waits for the world to change. Not because it hopes, not because it plans, but because that is what it is made to do. And in that waiting, a new kind of timeline emerges. If a microbe can sleep for millions of years and still awaken, then what is time to it? What is extinction or disaster, or the rise and fall of species, if the instructions for life persist unchanged in a place beyond reach? The sleep of microbes reveals that time does not erase, it simply delays. It's possible, even likely, that microbes from Earth's earliest oceans still exist today, unchanged in the deep. Not as living colonies, not as active life, but as seeds, as messages written in carbon and nitrogen, stored in the cold vaults of stone. And if life ever arrived here from another world, carried on a meteorite embedded in dust, then it may have slept in the same way, waiting, preserved in salt, frozen in ice, tucked into clay, invisible until the world warmed enough to call it back. What stirs a microbe from its sleep? A change in temperature, a trickle of water, a shift in pressure, the faintest scent of nutrient. That's all. That's enough. Like a key turning slowly in a lock, these conditions break the seal, and life begins again. Not as something new, but as something remembered. It is humbling to know that Earth holds such sleepers beneath our feet. Beneath deserts, beneath glaciers, beneath the floors of oceans no longer here. And even now, scientists drill deep into ice cores and salt domes, finding dormant life that predates humanity, that predates mammals, that predates flowers and forests and even fish. Not every microbe awakens. Some are too damaged. Some are too old. Some have unraveled completely, leaving only the ghost of a structure behind. But others endure. Others return. And they remind us that life is not a flame, but a rhythm. Can slow, can pause, can stop without ending. And perhaps that's why microbes matter so deeply to this story. Because if life traveled here from elsewhere, from Mars, from a moon, from some distant rock beyond the stars, it may not have arrived with fanfare or form. It may have arrived in sleep. It may have waited. And in that waiting, it may have shaped everything. And yet, if life can remain hidden in crystal for 100 million years, how much of our planet's past or another's is still alive, just not yet awake? All things drift toward disorder. This is the rule we call entropy, the universe's quiet pull toward chaos, toward the breaking down of patterns, of forms, of memory. Stars burn out, mountains erode, structures collapse, even thoughts fade. But still, something lingers. Even in a universe ruled by decay, certain patterns resist forgetting. The spiral of DNA, the mineral lattice of a shell, the stable orbit of an atom in a molecule that has repeated itself for billions of years. These are the places where memory hides. Not memory as recollection, but memory as structure, as a shape that refuses to dissolve. This resistance, this quiet defiance of entropy, is part of what makes life so strange. Because life, by its very nature, is temporary. It breathes, it breaks, passes, but beneath its softness, beneath its vulnerability, is something else. A stubborn pattern that keeps returning, keeps rebuilding, keeps remembering how to be. Even as the body fails, the code remains. Even as civilizations vanish, something in the molecules persists. And we call that persistence identity. You are not the same person you were 10 years ago. Every cell has changed. Memories have softened. Bones have shifted, but your DNA, your blueprint, your internal rhythm remains. The shape holds, not in spite of entropy, but alongside it. Because entropy is not the enemy of memory. It is its contrast, its foil. Without entropy, memory would not be precious. There would be no need for storage, no meaning in preservation. But because everything dissolves, the things that don't, the things that last become sacred. In the heart of this contrast, we begin to ask a deeper question. How does identity survive in a universe made of loss? A spiral of molecules, a chain of nucleotides, a sequence of atoms that somehow, against the pull of heat, radiation, gravity, time, remembers what to become, remembers how to divide, remembers how to replicate. Even when broken, DNA can repair itself. Even when scattered, its fragments can sometimes be reassembled. It is not perfect, but it is persistent. And perhaps this is what life is at its core. A set of instructions that refuses to be forgotten. Across eons, life has copied itself again and again, passing memory forward through touch, through time, through chemistry. From microbe to plant to animal to us. What we call evolution is not just change. It is the editing of memory, a sculpting of identity across deep time. And when we zoom out, past the level of cells, past the boundaries of species, we begin to see something even more profound, that the pattern of life itself has shape. Not one shape, but many. Spirals, branches, loops, feedbacks. These are not just metaphors. They are the geometry of survival, the forms that remain while others fall away. And if we accept that life may have started elsewhere, seeded from another star, carried in stone or dust, then the shape of memory becomes even more mysterious. Because it means that what lives inside us did not begin here. And yet it remains. It remembers its function. It remembers its path. It remembers, in form if not in thought, what it was designed to do. This is not memory in the way we usually imagine it. There are no stories, no scenes, no language, but memory lives in salt, in protein, in the twist of a molecule that learned, somehow, how to fold itself just right. And even entropy cannot take that away easily. Some structures, like viral capsids or extremophile enzymes, have remained nearly unchanged for billions of years. Their forms are too efficient, too refined. Evolution doesn't touch them because they've reached something like perfection. Not absolute, but sufficient. They are the fossils of function. And through them, we glimpse something fragile and eternal. The ghost of identity moving through matter. Entropy frays, but life patches. Entropy dissolves, but memory clings. Entropy forgets, but evolution re-remembers. So what is identity? Is it the consciousness we feel? The stories we carry? Or is it something quieter, the way a molecule curls, the way it binds, the way it endures through chaos? We are not exempt from entropy. We too will fade. But in our blood are patterns that predate Earth's continents. In our cells are sequences that remember oceans long vanished. In our breath are atoms that were once inside stars. And so we drift forward, delicate shapes holding their form in the presence of noise. And yet, if memory can persist without thought, could something else be remembering us? Even now, most fossils do not speak. They do not rise from the rock with stories on their lips. They wait in stillness, half-formed, half-erased, telling only what time has allowed them to keep. But sometimes, silence is the loudest thing in the record. The fossil record, for all its depth and richness, is more gaps than story. Layers of missing time. Entire ecosystems lost without trace. Strange disappearances. Sudden absences. Whole chapters torn from the book of life without explanation. We call them extinction events, evolutionary bottlenecks, incomplete strata. But what if some of those silences aren't accidents? What if, just once or twice across deep time, the thing that left no trace wasn't of Earth at all? There is a kind of quiet that feels different. A hollow not shaped by erosion or collapse, but by something that passed lightly, as if never meant to be seen again. Some researchers, cautious but curious, have asked, could there be fossils we don't recognize as fossils? Could something have left behind not bone or shell, but a pattern, a signal, a shape written in chemistry, not calcium? We assume all fossils belong to earthly life, that their logic follows what we know. But what if something older once touched this planet? Something with biology we wouldn't recognize, something with a timeline we've already forgotten. If such a presence once passed through our oceans or skies, would it leave a fossil? Or would it leave nothing? And if it left nothing, would we notice? There are strange moments in the geological record. Sudden blooms of complexity without clear origin. Fossils of organisms so unlike those before or after them that they feel like visitors. The Ediacaran biota, for instance, soft-bodied, symmetrical, ethereal. Life before the Cambrian explosion. Life that barely fossilized. Life that left us only the lightest of imprints. They do not fit easily into the tree of evolution. They do not persist. They do not return. And then, there are gaps. Long stretches of silence between life surges. Not just from destruction, but from disappearance. As if the earth took a breath and forgot what it was doing. These may be coincidences. Most likely they are. Geology is cruel to the delicate. The record we have is biased toward the hard, the heavy, the buried. Soft tissue dissolves. Microbes vanish. Only the lucky remain. But still, the silence feels structured. And structured silence invites wonder. Could something have left this world long ago, before stone had a chance to harden around its passing? Could the only fossils it left behind be not in the crust, but in the code? Tiny anomalies in DNA, unexplained functions in proteins, molecular fossils that live not in rocks, but in us? Or perhaps, it left behind nothing, because it didn't die here, it simply moved on. We often look for absence as evidence. But what if the most meaningful trace is the one that was never meant to be seen? A vanished visitor. A spark that came and went. A fossil not made of bone or tooth or shell, but of silence itself. Not because it failed to leave a mark, but because it was never meant to leave one. And yet, if silence is a kind of fossil, how many have we already stepped over, never knowing? Beneath the surface of the sea, far below the shifting waves, past the sunlit shallows and the dark, drifting trenches, there is another ocean. Not of water, but of life. Not a place we can swim, but a place that breathes in silence. It lies beneath the seafloor, beneath layers of sediment older than memory, a hidden biosphere stretching miles deep into the Earth's crust. It is not rich in motion. It does not sparkle or pulse. It does not fill aquariums or tidopools. Instead, it lingers. It waits. It survives in slow motion on timescales we barely understand. This underground ocean, made not of waves but of microbial colonies, holds more biomass than all the oceans above it. It is vast. It is ancient. And it is alive. Barely, but still alive. Some of these microbes take centuries to divide. Some have lifespans measured not in years, but in geological epochs. In the deep biosphere, energy is scarce. Metabolism slows to a crawl. Communication stops. There is no light, no predator, no storm. Only persistence. And in that persistence, something incredible emerges. A memory. Not one we can read like a book or a fossil, but a structural memory. A lineage of molecules that may have never stopped since the beginning. Life that settled beneath the crust when the oceans were young, and never left. Some scientists believe this biosphere may be the most ancient, continuous ecosystem on the planet. Not just a refuge, but a remnant. A quiet heartbeat echoing from the dawn of biology. Could this be where life first gained its rhythm? Not in the sky, not in the forests, but in the cracks of rock beneath the ocean, where heat and chemistry created just enough chaos to become organization. If Earth was ever seeded by life from beyond, carried in stone, in dust, in sleep, this is where it may have landed. Not on dry ground, but in deep water, where geothermal vents create energy gradients, where minerals drift and fold, where molecules test each other for compatibility in the dark. And maybe, once life took root, it found no need to rise. Maybe the surface, with its radiation and impact storms, was too unstable. Maybe the deep was safer, and so it stayed. It adapted to the pressure, to the cold, to the quiet, and it kept adapting for billions of years. When we drill cores into the ocean floor, we sometimes find signs of life more than a mile down. We find microbes feeding slowly on ancient carbon. We find DNA sequences with no known relatives. We find persistence without noise. And we wonder, what is their story? Are these organisms our ancestors, still dreaming beneath the world they helped create? Or are they something parallel, a separate branch of life that never surfaced? Either answer is humbling, because it means Earth contains not one biosphere, but at least two, one loud, fast, bright, the other dim, slow, and whispering. And the whisper may be older. The rock beneath the ocean is not uniform. It holds fractures, pockets, mineral veins, places where water flows and heat gathers. Life threads itself through these places like roots, but without plants, like neurons but without a brain. It is a network without beginning or center, a system that feels more like memory than muscle. Perhaps this is Earth's original memory, not stored in books or brains, but in sequences of carbon, sulfur, nitrogen repeated through time because they worked, because they endured. What we call intelligence may not apply here. There is no consciousness in this biosphere, no thought, but there is pattern, there is response, there is stubbornness, and sometimes that is enough to qualify as a kind of remembering. We have only begun to understand it. We cannot map it easily. We cannot see it with our eyes. But we know it exists, and we know it does not ask for us. It would continue even if we disappeared. And that, perhaps, is what makes it most profound. Because in the darkness beneath the sea lies something we cannot touch. A story that may have begun long before us, and will likely outlast us. A biosphere that speaks not in complexity, but in persistence, in presence, in survival. And yet, if the deepest part of Earth still remembers how life began, what dreams might be stirring in the rocks of other worlds? There is a reason we speak of life as carbon-based. Not just because it's true, but because carbon is more than an element. It is a storyteller, a quiet one. It doesn't shout its history, doesn't scrawl messages in stone, but it weaves itself into everything alive, and in doing so it remembers. Its atoms curl into spirals. Its bonds shape proteins. Its lattices become shells, bones, breath. Carbon is the spine of biology, flexible, stable, endlessly combinable. But it's also something deeper. It is the shape of memory itself, carried forward through time, from cell to cell, from planet to planet. We find it in every organism, in every fossil, in the soot of ancient fires, in the signature of something that once breathed and then turned still. But what if some of this carbon, this intimate thread that runs through all of us, did not begin here? What if it came from somewhere else? Somewhere older? Somewhere no longer burning? Carbon is born in stars. In their death throes, when gravity collapses and atoms are crushed together with heat and violence. It drifts outward in the shells of red giants, in the skeletons of supernovae, condenses in dust clouds. It gathers in nebulae. And eventually it becomes planets. Planets like ours. Planets with oceans and weather and lightning. Planets where carbon does more than settle. It starts to remember its shapes, to repeat itself, to spiral. So when we look at a strand of DNA, we are not just looking at biology. We are looking at geometry inherited from space. Cosmic grammar. The curls and loops of carbon, encoded not just by life but by time. Even the simplest carbon chains found in meteorites echo these patterns. Amino acids, ring structures, aromatic bonds, like fingerprints left by the stars themselves. So we begin to wonder, are we speaking a language older than Earth? Is the carbon in our cells fluent in the accent of another sun? Perhaps that's why life feels so familiar, even as it astonishes us, because its voice is not new. Its voice is old. It speaks softly, in repeating motifs, in symmetry, in function. And deep in its breath, it carries the rhythm of galaxies. Carbon never forgets how to bond. It remembers structure. It remembers shape. It remembers what works. And maybe that's the definition of life, not just motion, not just growth, but the ability to remember form. When we burn fossil fuels, we are igniting ancient carbon, the stored memory of forests, algae, plankton. But go back further and that carbon predates plants, predates oxygen. It predates land. It may even predate Earth itself. That's the strange comfort. The idea that what lives inside us now was once drifting in clouds of dust, waiting for the right temperature, the right pressure, the right kind of silence. And when the moment arrived, when Earth's oceans formed, when its atmosphere cooled, when its crust cracked open, carbon was already here, ready to spiral, ready to begin the story again. Not because it was guided, not because it was sent, but because carbon remembers how to connect. And that connection, from atom to molecule, from molecule to cell, from cell to species, is the quiet miracle at the heart of biology. Carbon does not act alone, but it leads. It is the spine, the scaffolding, the echo. And when we ask who we are really asking what has been carried forward, what has remained, what still whispers in our bones when all else is stripped away. The answer, perhaps, is this: we are echoes in carbon's spiral. And yet, if carbon can carry memory from one star to another, how far back does our spiral truly begin? Extinction is not silence. It is not an ending. It is an interruption, a fracture in the story, like a mirror cracked but still reflecting. We think of extinction as final. A species disappears, a forest burns, a reef crumbles to dust. But the deeper we look, the more we see that extinction never wipes the canvas clean. It smears. It scars. It leaves behind echoes, imprints, seeds buried in ash. There have been 5 great mass extinctions in Earth's history. Events so vast, so deep in time, that they redrew the planet's biology in a single breath. The worst of them, the Great Dying, at the end of the Permian period, erased over 90% of all marine life. Forests collapsed. Oceans turned acidic. The air itself may have burned. It took millions of years for life to return. But it did. Not as a repeat, but as a reinvention. Every extinction is a mirror cracked by trauma, and what returns is never quite the same. But here, in this cracked reflection, a strange question rises. What if one of these extinctions wasn't just an end? What if it created an opening for something not from here? What if, in the quiet that followed, something unfamiliar stirred? Not from the earth, but from the sky. This is not the core of mainstream science. It is an edge thought, soft and speculative. But the facts leave room for wonder. After the Permian extinction, life returned, slowly, unevenly, with new forms and sudden innovations. Creatures that had never existed before. Patterns that rose with startling clarity. The same is true after the Cretaceous extinction, the one that ended the age of dinosaurs. A single asteroid, perhaps just 6 miles wide, erased entire lineages in days. And yet, in its aftermath, mammals rose. Brains grew. Language eventually appeared. Not because something new came, but because something new was allowed. But what if it wasn't only an invitation to evolution? What if, as the earth cooled from its wounds, as fire became dust and dust became soil, something else arrived? Carried in the debris, in the ash clouds, in the meteorites that often follow large impacts like shadows. What if life, or something close to it, came with the rock that ended one chapter and began another? This is where the idea of panspermia reentry after extinction events begins. Not as science fiction, but as scientific possibility. Because mass extinctions destabilize the surface. They shake the crust. They punch holes in the atmosphere. They heat the oceans and change the chemistry of everything. And yet, in all that chaos, they also expose the Earth to the stars. They make space a little closer. They make landing a little easier. They offer a brief window when what falls from beyond might survive. Could a post-extinction Earth be the perfect host for seeds that had once been turned away? We already know that microbial life is capable of surviving in space. That some organisms can endure the vacuum, the cold, the radiation, sleeping, hidden, patient. We know that rocks move between planets, that Earth has received meteorites from Mars, and likely from farther still. And we know that impact winters are followed by slow, strange springs. So the thought lingers, could one of those springs have bloomed not from survival, but from arrival? It wouldn't take much. Not a civilization, not a creature, just a molecule, protein, a viral shell, just enough to mix with Earth's recovering biosphere, to alter it, to rewrite it, to share something unfamiliar. Maybe nothing happened. Maybe life returned from its own buried roots. But if even a single line of DNA was added from beyond, then extinction was not just destruction. It was transformation. It was an open door. And if that's true even once, then the history of life is not linear. It is not local. It is collaborative. A record written by many hands, across worlds, across epochs, across extinction and renewal and extinction again. And what does that make us? Survivors? Or inheritors? And yet, if life once came back from the stars, who's to say it's not still falling now? What if memory is not something we think, but something we carry? Not in the brain, not in stories, but in the molecules that build us, in the spiral staircases of DNA, coiled tightly in every cell, repeating a code older than language, older than Earth, perhaps. DNA is not just instruction. It is inheritance. It is remembrance. A pattern so precise, so persistent, it has echoed through billions of years of change. Through ice ages and extinction events, through meteors and migrations, through sleep and awakening. A thread of memory, unbroken. We often describe it like software, a set of commands. But DNA is more than that. Its shape, its rhythm. It's a memory that rewrites itself slowly, carefully, as conditions allow. A memory that edits but never forgets entirely. What you are, in part, is what has been remembered generation after generation, through every ancestor that ever lived. Not just human ancestors, not just mammals, but fish, worms, microbes, and perhaps something more distant, something no longer here. When we trace DNA backward, we arrive at common ancestors. But deeper still, we find structures shared by all life. Ribosomes, enzymes, metabolic cycles that remain almost unchanged, even across billions of years. Why? Because they work, and because life remembers what works. But where did the first memory come from? Where did that shape, that first curl of code, first arise? Some believe it formed in Earth's oceans, stitched together by chance and chemistry. But others, slowly, softly, wonder if that memory arrived from elsewhere. If DNA is a molecule shaped not just by evolution, but by journey. If its symmetry, its language of 4 bases, its double helix, its built-in mechanisms for repair, was formed under skies we've never seen. Starborn, alien, not in form, but in origin. If even a fragment of this is true, then our biology is not a solitary invention. It is a shared memory, a script passed between worlds, evolving not just through time, but through distance, through entropy, through silence. Think of a virus, a sliver of genetic material, wrapped in protein, seeking only to copy itself. Viruses are not considered alive, but they persist. Some are ancient, some are embedded in our own DNA, fossilized like echoes. Could they be memories from beyond? Could parts of our genome, long silent, long misunderstood, be molecular souvenirs from an earlier version of life? One not born on this planet, but inherited by it. We don't know, but the thought lingers, because some pieces of DNA don't seem to do anything. They don't code for proteins. They don't influence traits. They just exist, silent, waiting. We once called them junk. Now we call them non-coding regions. And slowly we're learning they are not empty. They regulate, they shape, they might even remember. So what is memory if not this? Not the recalling of events, but the repetition of form. The quiet insistence that something once worked and might work again. You are made of this. Every heartbeat, every breath, every blink. all governed by molecules whose structure was set long before you were born, possibly long before this planet had continents. You are the continuation of a memory written in atoms. And like all memories, it degrades, mutates, forgets. But some parts do not change. Some parts are too old to rewrite. Some parts hold the shape of a time before time. Maybe that's why certain things feel familiar without reason. Why patterns echo in dreams and stories. Why spirals calm us. Why stars pull our gaze. Maybe we are remembering something deeper than thought. Maybe the memory is not just in us. Maybe we are the memory. And yet, if DNA remembers across billions of years, what forgotten songs might still be playing softly in the code? Life begins in water. That much we're sure of. Before there were forests, before lungs and feathers, before even the simplest shells, there was ocean. Liquid cradle. Chemical womb. The place where molecules first learned how to remember themselves. But lately, a new question stirs. Quietly, softly, from the deep. If life began in water, whose water was it? We tend to assume Earth's oceans have always been here. That hydrogen and oxygen simply combined, rained down, filled the basins, and gave birth to biology. But the science of planetary formation tells a messier story. A hotter one, a drier one. In Earth's earliest days, the planet was molten, shattered, constantly bombarded. Too hot to hold an ocean, much less life. And yet, not long after it cooled, water was everywhere. Rivers carved canyons. Seas shimmered under volcanic skies. Chemistry had begun. The timing is suspiciously fast. Too fast, maybe. Which leads to a beautiful possibility. What if Earth's water, the very thing that cradled the first cell, didn't form here? What if it was delivered? Some scientists believe our oceans were seeded by comets. Others point to asteroids. Many of these ancient objects, drifting through the early solar system, were rich in ice, rich in organics, rich in the raw ingredients of habitability. When Earth was young, collisions were constant. Each impact brought heat and trauma, but also water. Some of it vaporized. Some of it escaped into space. But much of it stayed. And over time, it pooled, emerged, deepened. The oceans may not have been born. They may have been collected. And within that water came more than molecules. Inside some of the asteroids that still fall to Earth today, we find carbon. We find amino acids. We find the seeds of biology, frozen and quiet, waiting. It's not a stretch to imagine that some of those seeds arrived with the water. That Earth's first tide was not just wet, but pregnant. Zircon crystals, some of the oldest minerals on the planet, hold clues. Trapped within them are tiny pockets of fluid, over 4 billion years old. Salty, ancient, still intact. And in those fluids, we read chemical ratios that suggest oceans existed far earlier than expected. They whisper of hydrogen from beyond. Deuterium levels that don't match Earth's core, but do match icy bodies from the outer solar system. Comets, interplanetary messengers, foreign water. If that's true, even partly, then Earth was not just seeded with life. It was bathed in the memory of other worlds. Its oceans are not purely local. They are inherited, mixed, shared. And if water arrived from elsewhere, who's to say life didn't ride in with it? What we call primordial may already be a remix, convergence, a reunion of scattered parts under the right sun, at the right distance, on a planet just quiet enough to listen. Maybe the first cell rose not from Earth's own chemistry, but from something remembered in that ancient water. Because water is not passive. It holds charge, carries ions, it shapes molecular bonds, protects, it dissolves, it incubates, and if it came from another star system, it may have already hosted life once before. Maybe simple, maybe microscopic, maybe not alive, but close. Maybe all it needed was another chance. And Earth gave it one. So when we look at our oceans now, vast, glimmering, ancient, we see more than a surface. We see a memory, not just of Earth's own history, but of somewhere older, somewhere no longer frozen, somewhere now quiet. Perhaps every wave is a whisper from a distant comet. Perhaps every drop once fell as ice across a world we'll never know. It makes the ocean feel not just wide, but deep in time. A liquid archive of alien rain. A basin filled by the hands of the cosmos. And yet, if our oceans came from somewhere else, then what else might be floating out there, looking for a place to pool and begin again? Molecules do not belong to planets. They are not loyal. They do not root themselves in soil or bind to the names we give worlds. They travel, quietly, patiently, invisibly, through gravity, through time, through clouds of gas and the open breath of stars. Long before Earth was born, before the sun gathered its mass, molecules were already on the move, drifting between stars, forming in the wombs of dying giants, curling into complexity in the icy dark of interstellar space. We like to think of the ingredients of life as Earth's own. That glycine, the simplest amino acid, is something this planet learned to make in its deep oceans. But glycine has been found elsewhere, far beyond the reach of earthbound chemistry. We've traced it in meteorites. We've seen its spectral fingerprints in the clouds around forming stars. We've glimpsed it in the molecular chaos of nebulae, where atoms collide not randomly, but rhythmically under the influence of time and light and heat. This is not science fiction. It's astrochemistry, the study of molecules in space, not as fantasy but as observation. We know they form in the envelopes of carbon-rich stars. That ultraviolet light and cosmic rays help shape them in the cold spaces between suns. That ice and dust are not lifeless, but laboratories, low-energy, high-time environments where complexity begins to stir. The universe is not empty. It is not sterile. It is rich in potential. And the molecules that made us, carbon chains, amines, alcohols, sugars, they are not local accidents. They are migratory, ancient, stubborn. They survive radiation. They hitch rides on comets. They fall to planets wrapped in rock or frozen into crystal. We are used to thinking of migration as a biological act. The flight of birds, the path of whales, the human journey across land and sea. But molecules migrate too. And they've been migrating since before life had a name. Perhaps the story of life is not about one planet at all. Perhaps it's about caravan routes across the galaxy. Slow rivers of molecules flowing from cloud to star, from star to rock, from rock to ocean. Some settle, some vanish, some improbably survive. And in surviving, they remember. Because every structure that persists, every chain of atoms that repeats itself again and again, carries a kind of memory. Not conscious, not cognitive, but functional. A memory of bonding, of shape, of reaction. Maybe glycine forms again and again not by chance, but because it works. Because it has worked before. Because it remembers. We are built from this, from patterns so ancient they no longer feel like invention. They feel like inheritance. Like something borrowed and passed on. And if glycine can travel across light years, if sugars and alcohols and amino acids can endure the cold and silence of space, then what else might be migrating now? What else might be drifting, unseen, between stars? Maybe there are molecules we've never met, patterns we've never decoded, signals not in radio waves, but in chemistry, slow, unfolding messages written in atoms instead of words. Maybe life is not a miracle of Earth, but the inevitable outcome of enough molecular migration. A tipping point reached when the right compounds settle in the right place, warmed by the right sun. Not magic, not chance, just time. And so we begin to ask a softer question. Were the molecules that made us ever truly bound to this planet? Or have they always been travelers? And if we are made from travelers, does that make us passengers? Are we still part of that migration, a mobile memory, continuing the journey through biology, through thought, through language? And yet, if molecules can migrate across the galaxy, could life itself be nothing more than the memory of that migration, learning how to speak? You are made of dust, not as a metaphor, not as poetry, but as chemistry, as truth. Every atom in your bones was born in a star. Every trace of iron in your blood, every glimmer of calcium in your teeth, every carbon bond in your cells, all forged in the cores of ancient suns, long dead, stardust, scattered. And from that dust you came to be. But what if this dust did more than combine? What if it carried memory? Not memory with thoughts or images, but memory as tendency, as rhythm, as the way atoms fall into shape more easily than they should, as if they've done it before. What if dust could dream? Not in the way we dream, with symbols, with longing, but in the way particles persist. The way patterns repeat. The way molecules, time and again, curl into spirals, fold into proteins, reach toward the familiar warmth of replication. We don't often think of dust as alive. It lies still. It gathers. It fades. But before it settled here, it moved. It drifted through light years of space. It passed between stars, through shock waves and nebulae, through gravitational fields and radio storms. It carried with it the scars of ancient collisions, the static of forgotten supernovae, the temperature of voids no longer visible. Some of that dust eventually became rock. Some became planets. Some became water and air and flame. And some, the rarest some, became self-aware. It became life. So the question rises slowly. Did dust bring life? Or did life simply reveal what dust already was? We often separate the material from the meaningful. We say the soul is separate from matter. That thought is separate from chemistry. That dreaming is something more than atoms in motion. But what if there is no separation? What if dreaming is what dust does when given time? Think of a snowflake. Think of the symmetry, the complexity. Think of how it forms in silence, guided by nothing more than temperature and pressure and the subtle vibration of water molecules falling into place. Now think of DNA, of how it spirals, of how it folds, of how it seeks out matching pairs, how it divides, how it duplicates. Is it so different? What if life and even thought is simply dust, remembering how to organize? And if it remembers, does it also long? We speak of evolution as a process without intention. But maybe we're looking at the wrong scale. Maybe intention doesn't begin at the level of consciousness. Maybe it begins in the particle, in the subtle way certain paths are chosen, certain shapes preferred, certain energies held close again and again. Not because dust thinks, but because it has done this before. Because the universe has a kind of memory not as a mind but as a habit. Perhaps dreaming is not an escape from the physical, but the most intricate expression of it. When you close your eyes and drift into sleep, your brain replays fragments, images, emotions. It makes meaning from nothing. It assembles pattern from chaos. In a way, it's what the universe has always done. So maybe stardust does dream through us. Maybe that's what we are. The dreams of dust walking. The cosmos curled into a shape that can wonder where it came from. And if that's true, then every breath you take is a continuation of a dream that began in a dying star. Every thought is an echo of something older than planets. And still the dust remains, floating in space, drifting between galaxies, waiting, as it always has, for the next chance to spiral, to structure, to remember. And yet, if dust can become a creature who asks where it came from, what might it become next? Mars is quiet now, a red hush of dust and stone. The skies are thin, the surface cold, its rivers long gone. But once, it may have breathed. Once, it may have held oceans, clouds, currents, lightning. And in those moments, those brief early chapters, it may have known life. The Martian hypothesis begins here in the silence. In the evidence left behind not as voices, but as traces. Geological hints, chemical whispers, questions pressed into rock. What if Mars was once alive and shared, not just in theory, not just in distant possibility, but in fact in movement, in exchange, in origin? We have Martian meteorites on Earth, real pieces of Mars thrown here by impact and gravity held in our hands. Their chemistry matches the Martian atmosphere, a signature captured in glassy fragments. Some of them even contain strange structures. Tiny, worm-like formations once proposed to be microfossils. The most famous of these, ALH 84001, was found in Antarctica in 1984. Inside it, Scientists discovered carbonates, magnetite crystals, and odd shapes that stirred more than just curiosity. They stirred hope, doubt, imagination. Were they fossils, ancient microbes, or just geological coincidence? The question remains open, and quietly, it grows. Mars shows methane in its atmosphere not constantly, but in pulses. Methane is unstable. It shouldn't last long in open air. And yet it appears, reappears, fades, returns. On Earth, most methane comes from biology, from life. Could Mars have a deep biosphere? Hidden beneath its regolith, warmed by internal heat, protected from radiation? Could it still carry life today, not walking, not complex, but microbial, enduring, waiting? Or was it once fertile and then still? If life began on Mars before Earth had settled, the implications deepen. Mars was habitable earlier than Earth, cooled faster, formed crust sooner, may have hosted liquid water before our own planet was ready. Could life have originated there first? And traveled here? Through rock, through time, through the silence of interplanetary drift. Lithopanspermia makes this plausible. Rocks ejected by Martian impacts can reach Earth in months. Not all burn up. Some land. If even a single spore, a single viable microbe survived that journey, then the story of Earth's life may begin on Mars. Or perhaps, Mars was the receiver. Perhaps Earth birthed life and sent it outward. A reverse migration. A sharing not of civilizations, but of cellular heritage. A viral spark. A bacterial passenger. A seed hidden in stone. What matters most is not which planet was first, but that they were not alone. That life, once begun, does not obey borders. Planets trade more than gravity. They may trade memory. Even now, robotic explorers roam Mars' surface, rovers like Perseverance and Curiosity, searching for sedimentary clues, organic molecules, ancient lake beds. They read the rocks the way we read fossils. Gently, slowly, hoping for a story. And the story they seek may not be alien in the way we expect. It may feel familiar, because if Mars was once alive, then the life we find there might not be strange. It might be related. It might be us, a cousin in red soil, a forgotten sibling. The Martian hypothesis does not claim certainty, but it does ask us to widen our gaze, to stop thinking of planets as isolated experiments, and instead see them as participants in a wider system. A network of rocky worlds exchanging chemistry, sharing oceans, swapping seeds. And if Mars was once alive, and shared, then what other planets have whispered across space? What other worlds have offered pieces of themselves, and in doing so shaped our own? And yet, if Mars once gave us life or borrowed it from us, what would we owe it now that it sleeps beneath dust? Space feels empty, cold, still, untouchable. We imagine the stars like lanterns hung in a dark cathedral, each one distant, alone, flickering in its own place. But the universe is not as still as it seems. Its quietness hides movement. Its emptiness hides bridges. And so we begin to ask, can solar systems touch? Not in the way galaxies collide, not with violence or speed, but in softer ways, through dust, through drift, through long gravitational dances that unfold over millions of years. This is where the story of celestial bridges begins. It begins in stellar nurseries, those luminous clouds of gas and dust where stars are born in clusters. Here, suns ignite side by side, close enough to exchange material in their early chaos. Planets form nearby, debris flies, and in that youthful storm, a fragment from one world might drift into the orbit of another. Not instantly, not easily, but slowly, eventually, perhaps a planet, still cooling, still shaping its surface, receives a visitor. A stone, an icy core, a seed, not planned, not aimed, just caught in the swirl of a shared beginning. This kind of proximity doesn't last. Star clusters spread apart over time, pulled by the spiral arms of galaxies. But in those first tens of millions of years, when everything is soft, unstable, new worlds may whisper to each other through matter. We don't know how often it happens, but we know it can. We've found objects in our solar system, icy, elongated, oddly inclined, that suggest influence from far beyond. And then, in 2017, we saw something we had never seen before. Oumuamua, a long, thin object tumbling through space. It moved too fast on a path too steep to belong here. It was from another star. Not a comet. Not an asteroid. Not entirely explainable. But it was proof, the first we'd measured, that interstellar objects visit. And if one can arrive, so can others. And if objects move between stars, what do they carry? Dust. Molecules. And maybe, once in a great while, life. This brings us to rogue planets, worlds without stars, cast adrift by gravitational flings. They roam the galaxy alone, wrapped in cold, sometimes with atmospheres, sometimes with heat from within. They are not tethered. They are not still. And they are many. Some estimates suggest there could be more rogue planets than stars. Drifting between systems, slipping through the dark. Some may have moons, oceans beneath ice, hidden chemistry, a long, lonely time to evolve. Could they serve as bridges? Could life arise there? Or travel through them? And what if, now and then, a rogue planet passes near enough to a star system to send a fragment inward? A moonlet, a rock, a comet-like emissary. The journey might take millions of years. But space is patient. Gravity is a sculptor, not a brute. It curves the paths of objects, flings them outward, draws them back in. The orbits of planets wobble. Tails of comets reach. Trails of dust curl and fall across systems like threads in wind. These are the bridges not built but formed. Not engineered, but permitted. Rare. Fragile. But real. Could life or the instructions for life travel along them? The theory is not impossible. It is called interstellar panspermia, the idea that life, once begun, might not stay where it started. That molecules could cross not just oceans or planets, but stars. And that every system, every sun, might be part of a slow, vast exchange. Not a conversation, not a colonization, but a drifting dialogue of chemistry. Perhaps the galaxy is not a map of isolated islands, but a web of quiet contact. Each world adding its trace, each bridge leaving a thread, each encounter rewriting what life can be. And if that is true, even slightly true, then we must ask not where life began, but how far it has gone. How many worlds has it touched? How many fragments drift still, cold and asleep, waiting to spiral again? And yet, if the stars can pass messages made of dust, then what letters might be falling even now unseen into our solar sea? There is a quiet truth in nature. Patterns emerge. Not from control, not from design, but from chaos. From turbulence, from randomness, from time itself. Spirals in galaxies. Spirals in seashells. Spirals in DNA. Branches in rivers. Branches in trees. Branches in lungs. This is symmetry. Not the perfect kind, but the persistent kind, the kind that returns, repeats, echoes. And the more we look, the more we find it everywhere. In fossil curves. In the ratios of bone lengths. In the way leaves unfurl, storms rotate, embryos divide. And in the double helix of our cells, that endlessly folding ladder of life, coiled like memory. Why does nature favor these shapes? Why does life, across so many scales, seem to mirror itself? We call it convergence when different organisms evolve the same solution. We call it efficiency when chemistry favors certain outcomes. But maybe it's something deeper. Maybe these repeating patterns are not just results, they are reminders. Reminders of something older, something universal. What if symmetry is a whisper? Not from a voice, but from the structure of existence itself. A language not spoken, but shown. Patterns as messages. Shapes as stories. Curves that echo a shared origin. A moment when the universe first organized itself and never quite forgot how. The golden ratio. Fractals. Molecular mirrors. Self-similar spirals in hurricanes and horns and human hearts. We find these things not because we want to, but because they're already there. In the fossil record, We see it in the coiling shells of ammonites, the perfect tessellations of coral, in snowflakes buried for millennia, in mineral crystals shaped by ancient waters. In galaxies billions of light years away, we see the same structures, spiraling arms, star nurseries in filaments, rings within rings, the same shapes, across incomprehensible distance, across unimaginable time. Could this symmetry be a signature? A trace not of life as we know it, but of origin? We like to imagine that life emerged many times, in many places, that chemistry, given enough time, creates biology wherever it can. But what if it didn't emerge many times? What if it started once and spread? Not just through panspermia, not just through drifting stones or seeded oceans, but through pattern inheritance, through structure, through molecular memory passed across light years. What if life repeats itself not because the universe demands it, but because life is remembering its first form? We think of biology as open-ended, as improvisation. But perhaps it is more like a melody, improvising, yes, but always returning to a theme, always circling back to certain notes. What if symmetry is that theme? An echo from the first birthplace, whenever that was, the DNA spiral, the cell's lipid bubble, the nested loops of neural networks and coral branches and the spiral arms of galaxies. Over and over, across scales, across species, across systems, not because they're best, but because they're familiar. We call this the hidden symmetry of origins. A soft idea, a speculative one, but one that grows the more we listen, because symmetry is more than shape. It is memory made visible. A gentle insistence that the same answers appear again and again when you ask the right questions of the universe. So we look at a spiral in a nautilus or a sunflower or a strand of DNA and we ask, is this just physics? Or is this a kind of echo? Is it life repeating what it learned the first time? And if so, where and when was that first lesson written? And yet, if symmetry is a memory shared by all life, then what else might we carry silently from that first origin, wherever it might have been? If life began billions of years ago, who was there to see it? Not a person, not a mind, not even a memory, just the sea, just the stone, just the wind moving across an atmosphere still learning how to breathe. There were no eyes, no journals, no language to hold the moment, only molecules folding, repeating, becoming. This is the haunting idea we drift into tonight, the concept of time without a witness. A history not lost, but unnoticed. A universe perhaps full of life, unfolding in silence, never seen. Because the age of life is not the same as the age of awareness. Cells may divide for billions of years before they ever think, before they dream, before they build. And in that space, in that yawning stretch of unrecorded being, so much can rise and vanish. The fossil record on Earth only captures a fraction of what lived. Most of it is missing, eroded, pressed beyond recognition, dissolved into the ocean or recycled into rock. Entire ecosystems may have come and gone with no trace. And if that can happen here on our own planet beneath our feet, then what else has disappeared across the stars? How many planets bloomed briefly with biology only to be erased? How many living worlds flourished in their moment, rich with complexity, never knowing they were alone? Perhaps some were destroyed by impact, by entropy, by time itself. Perhaps some simply changed, becoming quiet again, folding back into geology. And perhaps some are still there, waiting. But what if they aren't? What if they never left any sign? A billion-year-old biosphere could be invisible now. Not because it failed, not because it meant to hide, but because the universe does not promise remembrance. Without witnesses, life is a whisper lost in wind. It doesn't need to be seen to exist. It doesn't require applause. It only requires chemistry and time. We may be the only species to look at the stars and ask who else is watching. But that doesn't mean others never were. Only that their watching left no echo we can trace. What if life is common, but visibility is rare? The Fermi paradox asks, if the universe is so vast, where is everyone? But maybe we're looking in the wrong direction. Maybe everyone was already here, long ago, and we missed them, because there were no witnesses, just biospheres blooming, vanishing, reshaping, sleeping again. Just oceans filled with thoughts too simple to name. Just molecules learning slowly how to persist. Earth, too, was once invisible, alive but unwatched, until eyes evolved, until minds began to notice, until the past began to matter. We are the witnesses now. But how many ages came before us without witness at all? And if life arises often, but intelligence rarely lingers, then the cosmos may be full of ghosts. Not spectral, not haunted, but biological shadows, forgotten siblings, species that never carved monuments, civilizations that left no satellites, just a sigh of atmosphere, a forgotten isotope, a buried protein chain. If they're gone now, who remembers them? Maybe no one. Maybe the universe does not need to remember. Maybe memory, like life, is fragile, temporary, local. And maybe that's the point. Not to be remembered, not to last, but to exist, even once in the flow of time, unwitnessed yet still real. And yet, if life once unfolded without a witness, is it possible it's still unfolding now, just out of reach, just waiting to be seen? The earth does not speak, not with words, not with voice, but it remembers. It carries memory in its skin. The layers of stone and sediment, ash and silt, fossil and fracture, stacked gently over time, pressed into pages by the weight of what came after. Geology is a diary, not written in ink, but in strata, not read with eyes, but with patience. Every layer a moment, every line a memory. Some are loud, volcanic eruptions, impact craters, extinction events. Others are whispers, a shift in mineral composition, a slight tilt in isotope ratios, a subtle fossil curled inside limestone. Together, they speak of a planet that has witnessed everything and forgotten almost nothing. So we ask softly, what does Earth's skin remember about the day life arrived? Not in legend, but in chemistry. Not in myth, but in the alignment of atoms and the scars left behind by something beginning. There is no clear entry, no fossil labeled first. But the rocks are not silent. In ancient formations like the Isua Greenstone Belt of Greenland or the Jack Hills of Western Australia, we find hints. Graphite embedded in banded iron. Carbon isotope ratios suggesting organic processes. The selective preference of lighter carbon-12 over carbon-13, a fingerprint of microbial metabolism. Zircons, over 4 billion years old, contain tiny inclusions, seal droplets of liquid, remnants of ancient oceans. In these, we find clues that water existed earlier than expected. And where there is water, life may not be far behind. These traces are not definitive. They are not shouts. They are the geological equivalent of a breath caught in crystal. But they tell a story of a planet that cooled just enough, that held just enough water, that caught perhaps the right molecular seed and began to change. Slowly, quietly, irreversibly, and in changing it began to write. Sediments settled differently. Oceans began to cycle carbon. Iron rusted in the presence of microbial oxygen. Sulfur began to fractionate in unusual ways. Life left its mark not with tools, but with touch, with biochemistry that altered the behavior of the planet itself. We call this biosignature not life, but the echo of life. Not the creature, but the consequences. Earth's crust is full of these quiet echoes, not only in fossils but in color, in oxygenation bands, in the red stains of iron, in the black shales of carbon-rich seas. Even the rise of continents is shaped, in part, by life, by microbial mats that trapped sediment, by algae that thickened reefs, by root systems that softened stone. Earth remembers not just life's arrival, but its persistence, its choices, its changes, its weight, and this memory is layered, complex like skin. Scar tissue from asteroid impacts, bruises from volcanic winters, wrinkles from tectonic shifts. It is not perfect. Much has been subducted, melted, erased. But even erasure leaves a trace. the absence of a layer, the warping of a fault, the missing fossils from a once-thriving reef, all become part of the story, and so we read the planet slowly, like archaeologists of time. We chip away, we measure ratios, we map layers, and in those layers we ask, was life always here, or did it come late? And if it came, did it come alone? Because some scars do not match the rhythm of the earth. Some shifts seem too sudden, too foreign, and we begin to wonder, did the first breath of life on earth come from inside the earth, or fall gently from beyond? Perhaps the crust remembers both, the internal stirrings of geothermal chemistry, and the quiet landing of molecules from distant stars. Perhaps life arrived twice, once from within and once from above, and together they began to write a new chapter. Not all pages are legible. Not all chapters survived. But the story remains, written in the folds of mountains, in the rise and fall of sea levels, in the stillness of fossils no larger than a grain of sand. And yet, if Earth's skin remembers the day life arrived, could it also remember something older, the moment before, when something waited to begin? Before the first cell, there was something, not alive in the way we understand, not dead, either, just waiting, stirring, assembling in silence, before membranes enclosed molecules, before genes passed messages, before metabolism whispered yes and no. Something moved, not with limbs, not with will, but with tendency, with rhythm. Tonight we drift into that shadowed time, the liminal space before biology. Not the tree of life, but the rootless mist just before the root. We call it prebiotic chemistry, but names are thin compared to what it was. Imagine a young Earth or maybe a young ocean on another world. Not barren but restless. Waters warm with geothermal heat. Minerals dissolving into tide pools. Lightning above. Hydrothermal vents below. In this strange soup molecules met. Not all at once. Not neatly, but through repetition. Through chance. Through billions of tries. Lipids began to form bubbles. Spontaneous little pockets, like thoughts without minds. Simple strands of RNA curled into shapes that could copy themselves, at least partially. Metabolic cycles, crude, fragile, began to flow, converting energy from one form to another. No cells yet, no walls, no nuclei, just islands of order in a sea of noise. And maybe that's all life ever needed to begin. A loop, pattern, a moment where entropy paused just long enough for structure to take hold. What came first? The genes? The membranes? The metabolism? We don't know. We may never know. Because what came before the first cell left no fossil. No imprint in stone. Only implications. But we can still imagine. We can imagine protocells, soft bubbles of fat that trapped random molecules inside. Some popped. Others floated. Some, purely by chance, captured something useful. A strand. A spark. A cycle. And they endured just a little longer. Long enough for variation. Long enough for the first whisper of survival. This wasn't life as we define it. It was the rehearsal. The dry run. The first act before the play remembered it was being written. And maybe it didn't happen just once. Maybe life, or almost life, started and failed, started and vanished over and over across countless warm pools and undersea cracks. Maybe the chemistry repeated itself again and again, until one configuration lasted. Long enough to copy, long enough to drift, long enough to change. And from that self-organizing breath came the first true cell. A membrane, a boundary, a logic. The moment when matter said, this part is me and that part is not. But before that, there was only blur. A liquid world full of gestures. Of molecules reaching toward each other, not with intent, but with tendency. It's humbling to think that the most complex creatures on Earth, whales, trees, people, can trace their lineage back to that blur. To bubbles in water, to strands of code not yet aware they were codes, to a time when life was not yet life, but a question beginning to ask itself. And if Earth held such a time, who's to say it hasn't happened elsewhere? On Europa, beneath its frozen shell, on Enceladus in plumes of heated spray, on planets orbiting distant suns with chemistry slightly different, but stories just as old. Perhaps on countless worlds molecules are still rehearsing, still testing shapes, still looping through possibilities in warm, silent water, waiting for the first cell, waiting for identity, waiting to become something. And yet, if life needed no beginning, only time to arrange itself, how many worlds might already be whispering in that precellular tongue? Did Earth know? Not with thought, not with language, not in the way we think of knowing, but something deeper, a recognition, a slow alignment between what was alive and what could hold life. This is the quiet heart of the Gaia hypothesis, the idea that Earth is not just a stage for life but a partner, a system that evolves in relationship with its inhabitants. A feedback loop of breath, rock, cloud, root, and ocean, adjusting over time to keep conditions stable, habitable, alive, not conscious like a brain, but aware like a forest. And so we wonder, softly, slowly, did Earth welcome life? Did it shift just enough to hold the fragile seed? Did it recognize something strange and make room? The Gaia hypothesis, first named by James Lovelock in the 1970s, suggests that Earth's biosphere, atmosphere, geosphere, and hydrosphere are not separate, but symbiotic. That life shapes the planet, and the planet, in turn, shapes life. We see it in the way plants helped oxygenate the sky, in how microbes helped regulate carbon, in how forests cool the air, and oceans buffer heat. Each life form playing a role not just in survival, but in balance. This balance is not perfect. It shifts, breaks, heals, but across deep time it persists, and that persistence may not be accidental. It may be relational. When life first arrived, whether from Earth's own chemistry or from another star, the planet was not yet ready. Volcanic, acidic, unstable. But over time something changed. Not just life adapting to Earth, but Earth adapting to life. Microbes began to alter the atmosphere, breathing out gases, changing the temperature, feeding the soil. And Earth responded. Feedback loops emerged. Systems formed. Too much heat, more clouds. Too much oxygen. Fire resets the balance. Too little carbon? Weathering slows. Volcanoes release more. Over billions of years, these systems wove together into something astonishing. A planet that keeps itself habitable. Like lungs breathing. Like a thermostat adjusting. Like a heartbeat syncing with a guest. Was it intention? No. But was it intelligence in another form? Maybe. Because intelligence doesn't always mean planning. Sometimes it means response. Recognition. Sensitivity. Earth responds. And if Earth responds, then we must ask, did it know on some deep geological level that life was here? Did it feel the arrival of biology as something worth protecting? If life was seeded, if molecules came from a meteorite, from a distant origin, then Earth's reaction matters even more. Because it would mean the planet made space for a stranger, adjusted itself to keep an alien seed alive. And that seed grew. It unfolded. It became everything from trilobites to trees to us. Not because the planet was neutral, but because it participated. And perhaps that participation still echoes in the biosphere today. In the mycelial networks that link forests like neural pathways. In the way coral reefs regulate pH. In the balance of gases that allows breath to exist. Gaia, as an idea, does not require magic. It requires only this, a system that feels itself, that adjusts for survival, that holds life not as a passenger, but as a co-creator. It's not a goddess. It's not a mind. It's a relationship. And relationships remember. Perhaps that's what Gaia is, Earth's memory of being alive. Its skin, its oceans, its air, all shaped by life, and still shaping it in return. And if that's true, then Earth is not just where life lives. It is part of life. Not host, not vessel, but participant. And that makes every storm, every bloom, every season, part of something larger. Conversation, a balancing act, a memory playing forward. So when we ask, did Earth recognize life? The answer may not be yes or no. It may be, Earth became life. And yet, if Earth welcomed a stranger's seed, could it still be listening for the next one? We always return to gravity, the quiet force that asks for nothing but holds everything, that curves the path of light, that binds moons to planets and planets to stars, that pulls comets back home after eons of wandering, that lets dust become worlds, that lets bodies fall into orbit or into each other. Gravity is the shape of attention in the cosmos. It does not push, it draws. It remembers everything that tries to leave. And so we ask now, in this soft, drifting moment near the end, could memory itself have gravity? Could the act of remembering shape the universe the way mass bends space? Not metaphorically, not just in feeling, but in form. Because what is memory, if not the gravitational pull of the past on the present? Keeps things from floating away. It holds structure where there would otherwise be noise. It lets us loop back to childhood, back to origin, back to first questions. In humans, memory binds identity. In ecosystems, it binds cycles. In DNA, it binds function across generations. And in the universe, could it be that we are not just remembering, but that the universe is remembering through us? After all, we are made of stars, of dust, of particles formed in ancient furnaces. The hydrogen in our bodies is older than the Earth itself. That material, shaped by gravity, burned into form, scattered into space, and later, after unthinkable time, was drawn back into new orbits, new worlds, new minds. Isn't that a kind of memory? Not with thoughts, but with persistence, with return, with repetition. Maybe the spiral of a galaxy is the echo of a previous pattern. Maybe gravity isn't just the attraction between mass, but the cosmos holding onto itself, refusing to forget. We see it everywhere. A black hole holding the core of a dead star. A comet returning every few thousand years. A planet settling into perfect balance with its sun. Even the spiral of our DNA, coiled, curved, gravitational in its own way, feels like a mirror of galactic motion. Large or small, matter curves toward memory. Perhaps this is the deepest symmetry, that the same force which lets stars orbit also lets minds remember, that gravity and memory are not separate things, but reflections, one for space, one for time, both drawing the past forward. And if that's true, if the universe, in some quiet, unspoken way, is remembering itself, then what are we? We who name the stars, we who decode fossils, we who record time and dream of before. Are we the mechanism of memory? Are we the part of the cosmos that circles back to look? Perhaps we are gravity's way of looping inward, of folding experience, of giving dust a way to reflect, not as destiny, but as motion, as pattern, as curiosity written into atoms. What if consciousness, this fragile flame behind the eyes, is not a random spark, but a gravitational lens? A way for the universe to see what it once was, to gather its stories, to hold its structure a little longer. What if every question we ask about origins is the cosmos remembering its own unfolding? Not because it must, but because memory, like gravity, is inevitable where complexity lasts long enough. And if gravity is always pulling, then memory is always reaching, for shape, for pattern, for coherence. And yet, if the universe remembers itself through us, what are we meant to remember next? Between the stars, there is silence. No air, no light, no orbiting moons or warming suns. Just vastness, stretching, still. A space so wide it feels like nothing could cross it. Not light, not memory, certainly not life. And yet, we ask, could life still leap? Not quickly, not loudly, but patiently. Quietly, could something alive, or nearly alive, drift between the stars? A spore, a seed, a strand of code, folded tightly into a speck of dust. This is the soft edge of panspermia's boldest dream, that life is not just a traveler between planets, or even between solar systems, but between dimensions of space and time. Because even in the quiet, the black distance between suns, the universe is not empty. There are waves, gravitational ripples, bending space itself, quantum fields that flicker with uncertainty, cosmic rays, dust trails, and the slow breath of dark energy. Could life, or the blueprint of life, move through this ocean of stillness? Perhaps not in the way we imagine. Not in ships, not in beacons, but in spores, asleep. Microbes on Earth have survived extraordinary things. Vacuum, radiation, freezing, crushing heat. They've returned from space missions alive after years in orbit. They've been found in salt crystals millions of years old, simply waiting. Waiting, as if time does not pass inside them. Could such spores, hardened by evolution and protected by stone or ice, survive the stretch between stars? Some believe the answer is yes, if there is a path, a ride, a current. Rogue planets drifting through interstellar space could carry them. Comet clouds tossed out of systems by gravitational chaos might fling them across light years. And perhaps most mysteriously, quantum tunnels, folds in the structure of spacetime, might offer shortcuts no map could predict. We do not yet know if such tunnels exist in ways life could use. But in physics, possibility does not vanish simply because it is hard to imagine. Even gravity, once thought to be slow and steady, now ripples in waves across the cosmos. We've measured them, tiny distortions from colliding black holes billions of light years away. And if spacetime can ripple, if the universe can vibrate, then maybe the quiet between stars is not silence after all. Maybe it is a carrier wave. And life, in its most compact, dormant form, might ride that wave. Not fast, not in numbers, but like pollen on the wind. It might take 100 million years, or more. But time is not a barrier when sleep is deep enough. Could spores use gravity the way birds use air currents? Could certain materials, minerals, shells, ice fragments, act as shields through the interstellar dark? Could life, as molecule, as whisper, move across dimensions we do not yet understand? These are not theories with answers. They are questions made of wonder, made of the same stuff that looks at a quiet sky and asks, who else? Where else? How far could we go, if we needed nothing but patience? Because that's what these spores would need. Patience beyond our comprehension. Stillness deeper than sleep. No will, no intention, only structure and waiting. But if they land, if by some miracle they find warmth, liquid, energy, they may wake. They may divide. They may remember how to grow. And perhaps once, long ago, one did. And perhaps someday one will again. Between stars, there is quiet. But quiet is not absence. It is potential. And yet, if something stirs in that stillness, who will be there to listen? At the end of all this drifting, the questions soften. Not because they've been answered, but because they've been held. Held gently, like a stone from a beach we can't name. Held the way you might hold a memory you're not sure is yours. So we ask, not with urgency, but with wonder, are we the echo or the first song? Did life begin with us? Or are we only the latest verse in a melody older than planets? It's easy to believe we're the beginning, that this is the first time matter has looked inward and asked itself why. That consciousness bloomed here, for the first time under the sun, in these forests, in this skin. But the science and the silence leave room for something else. Maybe we're not the origin. Maybe we're the continuation. Maybe life has bloomed before, elsewhere, elsewhen. Maybe we are the echo of something that happened long ago, far away. A whisper left behind in dust and water, in code and chemistry. A seed sent not with intent, but with inertia, with the gravitational sigh of a dying star. A melody carried not in sound, but in spiral. And maybe that melody took root here. Or maybe we are the first song. The first voice to rise from chaos. The first mind to wonder aloud. The first to look back across deep time and feel it pulling softly, like gravity behind our ribs. The beauty is we don't need to know. Not tonight. Not ever. Because both are extraordinary. To be the echo means we are part of something vast. That life is not a rare flame, but a migrating light, passed from star to star, from world to world, across gulfs of silence. To be the first song means we are the universe just beginning to find its voice. That we are the first stanza in a poem the cosmos is only now learning how to write. Maybe it doesn't matter which is true, because both carry the same message. You are not separate from the stars. You are what they remember, and you are what they now dream. Every molecule in you once drifted through fire. Every breath you take was made possible by the memory of oceans. Your bones are echoes of mountains. Your thoughts, shaped by entropy, yes, but also by pattern. Somewhere in your DNA, there are sequences that haven't changed in a billion years. Tiny messages passed along like offerings. Not because they mean something, but because they last. And that's enough. Life, after all, is not made of conclusions. It's made of continuity. The thread that doesn't break. The loop that closes softly. The structure that returns, even when forgotten. So maybe the universe doesn't care if we find an answer. Maybe it only asks that we keep asking, that we keep watching, that we keep drifting through thought, like spores on gravity. Because if we are echoes, we are faithful ones. And if we are the first song, we are only just beginning. So now, as your eyes grow heavy, as the thoughts begin to float instead of land, let the question be your lullaby. Not a riddle, not a puzzle, just a soft place for your mind to rest. Are we the echo or the first song? You don't have to decide. You only have to drift with it. Because somewhere between the stars, between the atoms, between the waking world and sleep, something remembers. And something is singing it back. Sleep now, and listen to the question.